Hello everybody and welcome to this tutorial of sampling and monitoring data using props. So I'll start with this presentation to clarify the idea of working with props, then we will go to practice. So we have a set of post-processing functions for sampling data. So we have different functions, mainly three: boundary cloud, internal cloud, and props. So our interest in this video is to talk about props. So all these functions work on the basis that the user provides some point locations. So we are precising point locations and the list of fields where we want to get the information. For example, defining points, then specifying pressure or velocity or turbulence parameters, and so on. So the function writes out values of the field are in these locations. So props, how does this function works? So it identifies the nearest cells to the probe locations that we defined, called also point locations, and it writes out the cell values. So the data is written in a single file in time value format. So we will see this file in practice, and it's suitable for plotting graph. So generally, props is more suitable for smaller numbers. For example, if we have 5 props, 10 props, 20 props, it's okay. But when we have a large number of locations, it's preferable to work with boundary cloud or internal cloud. So I'll show you how to set props in static mesh and in dynamic mesh using two methodologies. So we will talk about monitoring props during the simulation, and the second one is after finishing the simulation. So let's start now with the practice. So here I start with the static mesh. For the first method, I choose this tutorial of Bits Daily. So here we have the zero folder of all the input parameters, constant, and system. So just to show you which solver, it's PisoFoam. It's PisoFoam. So the first method is to assign to precise our props in the control dict in system folder. So we are adding in the end of this file a paragraph section of functions. So we are defining functions. We are naming this function props. Then we define its type, props, in the library libsampling.so. Then for writing control, it will write each time step, then intervals also each one. And for the fields, it's pressure, and the probe locations, we are choosing these points to be probed. So this is very simple to do. Just add this section, precise the fields you are interested in probing, precise here the probe locations, the point that you are interested by getting the information in. Then here it's standard, you can just copy these two lines, and here you can specify, for example, other values depending on your need. So now I'll run the simulation. So I'll execute all run. And you can see that here we have post-processing folder, new folder created in Bits Daily. We can open it. It contains probes 0 because it's the starting point. For example, if here we are starting from a folder named, for example, 100 or 1000, it's our initial value. We will get here a folder named 100 or 1000. So here you can see that in the first lines we have the ID of the probe 0, so it's 0 here, probe 1, 2, 3 to 6, and also the coordinates of each probe. Then here we have time in this column, and here we have the pressure in each probe depending on time. So it rises for each time step the pressure, and it continues refreshing each time this file. So I'll stop the simulation here because I'm not interested in the results. I just wanted to show you how to probe pressure in defined locations. So I stop the simulation here. This is the first method, is to assign the function probes in control dict file. The second method, for the first method, we are working during the simulation, so the pressure is calculated while running the simulation. For the second method, we have, for example, if we already have the results, then we need to execute the probe function. So here, let's just go, it's the same example, just I'll run the simulation. Here you can see that in control dict I don't have the function of probes, so I'll run the simulation here. So here I have new folders created for results. I stop the simulation here to show you how to execute probes after the simulation. So here the difference that we created another file here in the system folder called probes1. Probes1, so we have the specification type probes. We can name it here probes. I named it probes1. You can name it as you like, probes2 or whatever. And here we specify the type is probes. Then the library, it's the same setup that we put in control dict earlier. So here it's a file to execute after finishing the simulation. So here it's the same thing. Then fields B, the probe locations, we define the points. And for executing this file, we need to run the command postprocess function. Then I need to define the name of the file probes1. Okay. So here you can see that we have a new folder created in our Bits Daily case called Postprocessing. We can check it. It contains the pressure file, but in this time it contains only for the folders. Let's see here. We can, yes, so For the time here, we are not recording for each time step, but it looks in the results folders here, and it looks for the nearest cell, then gives the value of pressure in this point. So it's compiled from the folders here, differently from the method one, where we had the pressure for each time step. So here we have only for the recorded folder. So this is the difference between the two methods of processing the props. So this is for static mesh. Let's now move to the dynamic mesh. Here I have sloshing tank 2D case. And we have here in control dict, I'll use the first method. I just eliminate this one because we are not interested in this case. So here we are precising probes, the same idea as the first test in static mesh. So here the additional line is fixed locations false, because as you know, in dynamic mesh the mesh is moving. So the locations, when we fix the location, so it may gives for example non-value, because the mesh is moving and we are looking for the pressure here. We are looking for the pressure in a void domain. So we just need to specify fixed locations false. So these points will move with the mesh and will be variant according to the reference of the mesh. Hope it's clear. I'll run the simulation here to show you. So here I'll stop the simulation, then I'll run OpenFOAM to show you. Apply. So I'll precise the grid, the X grid. So for the point, the specified point in the control dict, it's in 0, 9.95 and 19.77. So it's in the 9 here and 19 here. So you can see that if we just choose fixed locations equal to true, we may, in this case, in this time step, we may be here out of the domain, so we cannot get the pressure in this location outer of our mesh. So this is the idea why we are including fixed locations false, because it will get for each time step a new reference where it computes the pressure, the field that we need. We can go here in the post-processing probes. It will be the same as we saw, so probes 0, probe 1, and here time, and we have the precision of each time step. So this is for the first method applied on dynamic mesh during the simulation. What if now we want to apply the second method that we saw in static mesh in our dynamic mesh? So now we will do the same. Dynamic mesh here. Then we will go to System, Control Dict, and we will copy this section of props in a new file called props1. So I have it already in my folder. Just to show you, props1, then we will execute it using postprocess. I rename this folder of postprocessing. Then I'll run new terminal, open in terminal, postprocess function, and I'll name my function props1. So a new folder is created here. We can check it. So you can see that we have a folder for each file. Then let's check the file. So as you see here, we have a very high pressure in each props, which is not normal. So let's check the terminal. Here we have foam warning again. So did not find location in any cell, skipping location. So after finishing the simulation, as I showed you in OpenFOAM, perhaps in a precise time step, let's run OpenFOAM again just to explain it clearly. So here we have our solution. This is alpha water, pressure precisely. So this is the pressure. Apply. Okay, pressure P. So we can run it. So for this time step, I'll accord the grid. So when moving, yes, so you can see here. So from 9 and 19, it must be here. So the point is out of the domain. Even when we are recording this time step in the folder, even if we have already the results, but we have it in this domain, we are just like looking for the pressure in an empty location, an empty point. So this is why we have this error, did not find location. It's okay to do it during the simulation in the control dict as we did it for the first method. Here, system, control dict. So it's okay because this is during the simulation, so the location is updated and the reference frame is also updated in each time step. So it looks for the point in different reference. But when we have the results already computed, it's impossible to get, for example, this point in this time step, since this is an empty point and the domain is moving in this place. So here, for example, when going to another time step, we can catch, for example, in this time step, we can catch this point because it belongs to the domain. For example, if we check the terminal, we're gonna see that we don't have the same error for all the time steps, because there are some points that belong to the domain after the simulation, after finishing the simulation, and other points that are out of the domain during some time steps. So for example, here we can see that we don't have this error of did not find location in the in time step equal to 35.5. So let's check post-processing 35.5. So we can look for the pressure here. It's equal to 93668. So it's a logical value. But when going, for example, to the previous value of pressure, we will see that it's very big, which is not logical, and this is due to the movement of the dynamic mesh, and the cell couldn't be the nearest cell to the probe couldn't be identified for each time step. So hope it's clear in your mind. So this is all for this video. Thank you for watching, and see you in next videos.